The nature of natural variability. This is our first example to delve into the nature of natural variability. For this example, we use the F value to look at the nature of natural variability. So we're going to do an example with some simulated data to dig further into an ANOVA table. What do you need for this example? Very easy. You need your data, in which case we're going to do simulated data, and you need your ANOVA table. In this example, we have the outcome as the yield, and we have three treatments. We've got fertilizer, which is a 2-level factor. We've got soil, which is a 2-level factor. And we have variety, which is a 3-level factor. So we're going to look firstly at what a small F value means. Now, here we've just got an ANOVA table, within it our fertilizer against our yield. We've got our F value, which, if you remember, is the difference, or is the mean squared fertilizer divided by the mean squared residuals. Our mean squared fertilizer is 1.604, and our mean squared residuals is 20.480. Because the mean squared residuals is so much higher than the mean squared fertilizer, this means we have a very small F value. So what does this mean? Well, our fertilizer variable accounts for a very small amount of variability in the yield. This is evident by that the fertilizer mean squares is very small compared to the residual mean squares. The variability in the residuals should just be the variability that you get by chance. If we have accounted for all variability in the yield, the variability in the residuals is just random natural variability. A low F value suggests that the variability that's occurring in the factors, so in our case, this is in the fertilizer levels. So a low F value suggests that the variability in the fertilizer is less than what occurs by chance, i.e. the variability in our residuals. This is unlikely to happen randomly. This indicates that the residual variability includes some systematic non-randomness in there, that it's not entirely natural variability in our residuals. It implies that there's unaccounted variability in the residuals that could be accounted for with additional information. Fortunately, we can add another variable to our ANOVA. So we add soil to our ANOVA, and we have that alongside fertilizer. We notice now that there's one thing. The variability accounted for by fertilizer is still very low, but for soil, it's much higher. It's 100 times higher. Well, if we want to look at it that way. What does this mean? Well, an F value much greater than 1, such that we have with soil, where we have 9.49, this F value being much greater than 1 implies that the variability in the soil variable is much greater than the variability in the residuals. This suggests that the soil variable accounts for a good amount of variability in the ANOVA. However, in our situation, there's still a lot of unaccounted for variability. We look back at this, we see that we still have roughly roughly 80% is still unaccounted for. So let's add variety to our ANOVA. Remember, this is simulated data. So we add in our variety, and lo and behold, we now have not only our soil has a much higher F value, but our variety has a very high F value. So this F value has increased for everything. And that's not because of anything other than that, basically, if we look at our sum squares residuals, our degrees of freedom, our sum squares residuals, sorry, is now much smaller because our sum squares for the other three are much higher. mainly because we've now added in variety, which counts for 769.43. This means that our sum squared residuals is now much smaller. We still divide that by our 46 degrees of freedom, which means that our mean squared error is much smaller, which means that our F values are much bigger because we're dividing them by a smaller value here. That being said, well, firstly, between all of our variables, only 5% of variability is now unaccounted for in the data. This is great. Fertilizer accounts for more variability now, but it's still very small. We have a look back here. Our F value for fertilizer is roughly 1. A little bit more than 1, but roughly 1. So we've covered what happens when our F value is very small. That when the F value is very small, that implies that there is unaccounted for variability in the ANOVA. If the F value is very large, that implies that this is a variable which is accounting for variability in your ANOVA. What if the F value is roughly 1? Well, that implies that the variability in the factor, so in our case in fertilizer, the variability in fertilizer accounts for as much variability as if it was happening by chance. It may account for variability in the yield, but the more important thing here is that because it's roughly 1, this is implying that the variability, that all of the variability in the model has been accounted for, more or less. And having an F value around 1 kind of implies that we're probably left with just natural variability. Variety accounts for a very large amount of variability. The F value is very large, and the percentage of variability that variety accounts for is 78.1% alone in one variable. I mean, this means that a large portion of the fluctuations in the yield comes down to the variety used. This is really useful to help see which variables are impacting yield. And it seems, in our case, that variety is really impacting yield. A good next step is to actually look at the data, such as the means, to see how our different varieties impact the yield. Which is better? So here's our 3 varieties, and we can see how they are impacting the yield. We can see on average, the yield is highest for the 3rd variety. This seems pretty reasonable. So our ANOVA tells us that there's a difference, but our graph can tell us what that difference is. This is what we discuss more in our visualizing section about the nature of natural variability later in this topic. So overall, the F value says a lot about variability in the outcome variable. Remember, this is simulated data, and we've exhausted all of our variables. So I know, because the data is simulated, I know how we created our yield. So I know that the remaining variability is actually always, is here when we put the 3 in, the remaining variability is our natural variability. We don't usually know this in real life. I mean, in real life, data's not simulated. So you can never know for certain if the remaining variability is natural or if it's a mix of natural and unaccounted for. Using these looking at the F value, particularly if it's much less than 1, as we saw in the first case, is a great way to help determine or help indicate how, if there is still remaining unaccounted for variability. And we look at this a bit more in the next video on dummy variables. So this 48.41 residual variability is our variability that's left over. It has some natural variability in it. And as I just said, when the data is not simulated, we don't know if this is just natural variability or if it has some variability that could be accounted for by unmeasured variables. Thank you very much.